This desolate landscape, Haleakalā crater, is located on the Hawaiian island of Maui. It looks very similar to the distant, pockmarked wastelands of the moon. And it is here, at the Lunar Observatory, that NASA and the University of Hawaii are involved in work which helps us understand the geophysical science of the moon and the Earth. Lunar Observatory, situated at the 10,000-foot summit of Mount Haleakalā, uses laser technology to accurately range within 1 inch the 240,000-mile distance between the two bodies. Ranging, or measuring distance, is accomplished by clocking the time it takes bursts of laser light to leave the observatory, hit one of 4 retroreflectors on the moon, and return to the observatory. By measuring the continually changing distance between the Earth and Moon, we are able to unlock many details relating to the motions of both bodies. Analysis of day-to-day changes in the Earth's motion helps scientists better understand the Earth's rotation, continental drift, weather phenomena such as the El Nino effect, and forces deep within the Earth that set off earthquakes. There are currently 2 other observatories located around the world which also participate in lunar laser ranging, but as yet neither has achieved the level of precision of the Lunar facility. Much more will be learned in the future by interpreting data from many stations simultaneously. The accuracy of ranging has come a long way since Apollo astronauts Armstrong and Aldrin placed the first retroreflector on the moon. A member of the technical staff at the Jet Propulsion Laboratory working on lunar laser ranging is Dr. Skip Newhall.
The moon reflectors are composed of an array of several dozen or perhaps a few hundred of these so-called corner reflectors. And they have the nice feature that no matter what direction the light goes in from, it always returns out at exactly the same direction. So when we shine a laser beam at the moon, no matter how it's oriented locally, the light comes right back out. When the Apollo astronauts first put the reflectors on the moon, we got some returns back in early 1970 and late 1969. The uncertainty in the return time was about equivalent of a distance of 150 to 200 meters. That's around 600 feet. We have refined the timing equipment, the lasers, and the other associated electronic equipment that supports this. So now we have the uncertainties in distance are equal to about 3/4 of an inch, which is an amazing improvement.
The key to the lunar ranging operation is a laser that can be adjusted to create intense billion-watt pulses of energy that makes its way to the moon and back. The light energy is channeled out of the observatory by this mirrored instrument, which keeps the laser beam continually locked on target with the retroreflectors on the moon. Meanwhile, in the observatory's main control room, the receiving telescope, which is composed of 80 lenses, is adjusted to line up visually with the moon's Apollo 15 retroreflector near Hadley Rill. The giant telescope acts as a collector for the particles of laser light that make the trip back to the observatory. The time it takes for the light particles to reach the telescope is calculated and fed into data banks. The information returned is analyzed regularly by a group of scientists at NASA's Jet Propulsion Laboratory in Pasadena, California. Again, Dr. Skip Newhall.
We have now a means of measuring Earth and lunar phenomena, geophysical, body-oriented science phenomena, that were not available by any means before. This is the only way we can measure, particularly connected with the moon.
Lunar laser ranging, helping scientists to learn more about the Earth and our closest celestial neighbor, the moon.